Good morning, everyone. Myself KHUSHANGI KRIPLANI, second year BTech student of PCA. Today, I will be discussing applications of PCO with all of you. So, let's begin with it. Before that, I would like to give a brief introduction about what is PCA. PCA is basically a strategic procedure of unsupervised learning algorithm, which basically reduces dimensions of a dataset while preserving the most important patterns or relationships so that we don't have to store the exact bigger data. Instead of that, we can store some amount of data which eh, encounters uh, most important things which is needed to represent the data. Now, how to proceed with principal component analysis? Assuming that I have n data vectors of dimensionality d. Now, I want to reduce the dimensionality of this matrix. This is the main procedure of the PC. I want to reduce it to a size of matrix n, which is very, very smaller than d here. Now, I will search for the orthogonal directions of the space vectors m at least this vectors so that I can project my data on this m orthogonal directions or vectors. The structure of the data vectors is a sample covariance. The covariance matrix is formed in the PCA. Now we are finding the covariance matrix from the principal component directions. So how do we do that? We can do that by considering this, like I want a empirical covariance matrix. This is formed by concentrating the matrix and making it a zero mean matrix. Now subtracting the mean of those matrix, the row, like I have x1 to xn, I will find out all the mean matrices. This is the mean matrix. I will be subtracting the xn minus x bar and taking transpose. That matrix I will be getting it as a covariance matrix. That to a symmetric matrix, like the matrix will be kind of this matrix. Now this and this are same in the covariance matrix. The covariance matrix is formed basically by this, by making it the zero mean matrix. By transforming the current matrix, I am getting the covariance matrix by subtracting the mean of all the respective rows from the respective rows. X bar is the mean, and with this, I will be getting the some amount of eigenvectors. I will be selecting m highest eigenvectors out of it, the largest largest eigenvectors of all the sorted vectors. These are the principal components that I will be taking for the dimensional reductions. Now, after considering the m eigenvectors, I will be reducing this matrix into like I will be reducing the current matrix into d cross m matrix. Now, the d-dimensional vectors can be presented by projecting them into the m-dimensional Z. Now I will be using the principal component analysis and finding, according to that algorithm, I will be finding the data covariance matrix and reducing the d-dimensional data to m-dimensional data. So for the data covariance matrix, I have C is equals to 1 by n and this matrix given here by subtracting the mean of all the rows from the respective rows and taking transpose and multiplying the matrix I get is the covariance matrix, which is of the form U sigma U transpose. This resembles to the spectral decomposition. Now I want to reduce it. So I'll be taking the m largest eigenvalues of this covariance matrix. So this is reduced or approximated to 1 to m. This is the m up to m column or m rows matrix, reducing the dimensions from d to m. Now this is the orthogonal vectors. U and U transpose are orthogonal vectors. So we know that U transpose into U and U transpose is 1. Sigma is the matrix of the type like lambda 1, lambda 2 up to lambda m. These lambda m are the m largest eigenvalues of the covariance matrix. Now I project the input vector x to this subspace. The vectors I have got is U and U transpose into x. This is of the form like this is x, this is U transpose of this is n cross 1, 1 cross 1 cross m, m cross k, let it be Z C is something U transpose X. This is the projection of X into the subspace I have reduced to the subspace of the PCA. Basically, in the PCA, I am finding the direction vectors of M direction vectors. Now, how am I deciding those M direction vectors? I am suggesting those vectors that maximum of the points lie on those vectors. So I need to minimize the perpendicular distance, this blue distance, or either I want to maximize the scatter of the green points. This is the same thing by the Pythagoras theorem. Like if I minimize this blue distance, automatically my green distance will increase from the origin or from the scattering points. So for the PCA, I basically reducing my blue distance, the distance between red and green points, or I am maximizing the scatter of my green points. So basically in the PCA, I am projecting my data onto a lower dimension space. Now I am approximating a vector x. I am finding a approximate matrix of x bar here. Now I want this to be precise and as much as possible. So I need to reduce the loss function here. This is the loss function. This is my original matrix and this is my approximated matrix. So the difference between them should be as least as possible. The difference between them is as least as possible when the first m components of the eigenvectors are the maximum eigenvectors possible. In that case, I get the projected vector as this and this. This is the same thing actually. Now we come on to the most important part of this video. This is the applications. This is where applications of PCA play a most wide role. Eigenfaces. Eigenfaces is based on the principle of VC or SVD, anything. That is the same thing. So here we are given a data set. Here I am taking XCL data set. Now I am given a data of 38 persons. Now they are also projected under 9 different light directions or light formations. 64 images of each of them are formed with some pixels like m cross n. Each image of this size is m cross n. And every picture, every person has 64 images formed under different light conditions or facial expressions, anything. So I will be transforming each of the m cross n for each person into a long column vector. One m cross n type of of column. Now I have 64 columns for each of the 38 people. That many columns will be formed of pixels like m cross and will be 192 cross 89, 189, something of the sort. So I'll be proceeding with the code. Uh, Here in the case of the eigenvectors or the eigenfaces, we are first seeing the first 36 images of the people. First 36 people, and next we are seeing the 64 images for each person. Now we'll be transforming each m cross n, the pixel matrix. These are the 64 images for each of the 38 people. Now I'll be transforming this m cross n to a long column matrix and stacking all those columns together. Now I'll be seeing what the first two eigenvectors give me. The first two eigenvectors take into the consideration of the maximum covariance data, which is the most similar things among the almost all of the data, which can be the oval face structure, the eyes, nose, lips, not more specific features, but the most common features that are possible. Now here, for the prediction of the 37th phase, I'll be taking consideration of the first 36 images. The 37th phase would be formed by by projecting those x vector to UR vector here. UR vector where R is the rank. Here R is the rank of these matrix. The recognition phase is I would add the first mean phase which I subtracted. Then I would multiply those transform phase and U transpose. Like I would take the first R largest eigenvectors or eigenvalues, then form the phase from that, which is the prediction of the 37th phase from the eigenvalues of the weight matrix formed from the first 36 phases. So as I increase the value of the R, which takes into account the most different or distinct features amongst the phase possible, I will get the formation of the 37th phase. For the first two images, like first when the R's value is 25, like this is the original image I should get. When R is 25, this looks nothing like the image that it should be. When I increase R to 50, it somehow is coinciding with that. R is equals to 100, R is equals to 200. Now at R is equals to 200, it kind of resembles the original image. At R is equals to 400, this is a phase changing part where it mostly resembles to the original image. As I increase R, this coincides more and more towards the increasing image. Because of this R, I do not need to store exact large data for each of the 37 or 38 images, like which is 200 for 24,000 sets of images and pixels. Instead of that, I need to store some amount of R which considers the most important features which can form another images. Now here I am taking account for the two different persons, and when I take two different persons, they form clusters. They differentiate or classify themselves accordingly. Your person, I'm plotting to person 2 and person 7 according to their features. I can see the clusters formed. These are all black clusters formed by the person 2 and and red parts formed by the for person 7. These are the clusters made by the projections on the PC modes 5 and 6. Now here I took 5 and 6 instead of 1 and 2, which is most important because if I would have taken 1 and 2, this would not have been this clusters, because 1 and 2 consider it most covariance data, which is most similar amongst themselves, that could not differentiate. Clustering is evidence of differentiation. As I increase the value of R, like 5 and 6, as I go on increasing them, they can form clusters. I can play with them. Anyone can play with the code and see how clusters get formed between any random persons. So that's all for the eigenfaces code. The also place where PCA plays a very important role. PCA performs as autoencoders in some certain conditions. Now, what are autoencoders? Autoencoders are a special type of forward neural network which does the following: like it encodes the input from Xi and gives it into a hidden representation H. Then Xi dash decodes the information from H. Now the model I am forming is to reduce the difference between the approximated Xi and the Xi I originally have. H is a function of G which takes input of Xi and gives H. Here I have Xi of the form Xi or X is of n cross 1 dimension, W is of d cross n dimension, so I get H of d cross 1 dimension. And for the Xi bar, I have H of d cross 1, W star, which is W transpose of n cross d, so I get Xi of n cross 1 dimension. So here basically I am reducing the Xi information, like the dimensionality of H is less than Xi, and then I am decoding the information from H to Xi, Xi cap, which is my approximated Xi. So here I am taking into consideration the most important D out of the N information of Xi, from which I can get Xi bar, which is similar to PCA. Like I am reducing the dimensionality, taking into account only most important eigenvectors or eigenvalues. Now to prove how under what circumstances autoencoders and PCA are equal, let's proceed to the next slide. We now see that the encoder part of an autoencoder is equivalent to PCA only if I use a linear encoder, a linear decoder, and the square error loss function and normalize inputs. These are the most important conditions. Here I need a linear encoder and linear decoder. W and H should be linear functions, linear transformations of X. And I have used the square error loss function, like X minus Xi cap square. This is my square error loss function. And then my input should be normalized. Now, why is that? Let's come to that. Now, in this, I am normalizing the inputs like Xij minus 1 by m, Xkj. This is the mean. This is my mean, and this is the normalized part. Now the data has now been a zero mean along each dimension of x. Since we are subtracting the mean. This is my x dash. This is my x. Now I have x is equal to 1 by root x dash, 1 by root m of x dash. Now I have x transpose x upon, which is equal to 1 by m x dash transpose x dash. This is my covariance matrix. Now, without normalizing this, I would not have got my covariance matrix. The covariance matrix plays a very important role for the PCA. So, normalizing is very crucial for the covariance matrix of the PCA. Now here I have assumed that I already have a linear decoder and a square error loss function. So my square error loss function here is obtained when we use linear encoder. I now have to reduce this. I have now to reduce the square error loss function and make it minimum for the uh, procedure. Now I got x minus hw star whole square. Now I want to minimize this. This is also Fourier's form of Fourier's norm. I want to reduce the Fourier's norm. From the SVD theorem, I know that the minimum solution possible is when HW star is equal to the SVD of the matrix up to the k most important vectors, eigenvectors or the eigenvalues. U k less than equal to k, sigma k cross k, and V transpose less than equal to k. This is possible only when HW star is equal to the SVD of the matrix given, matrix X. Now I can, by matching the simple variables, that could be so different solution possible also. But here I am taking H to be U sigma and V star to be V transpose less than equal to K, which is the K important eigenvectors. So I had V transpose V as identity matrix. So ultimately I get something like this: X V sigma transpose U transpose into U sigma transpose U transpose inverse. U goes from this less than equal to K sigma K cross K. Okay. Now this is inverse. Now I can write that U transpose inverse sigma transpose inverse and U inverse. U something something to K sigma K cross K. X V sigma transpose U transpose. This goes to be identity matrix. This is initial k columns or the k rows of identity matrix. This I less than equal to k sigma k cross k. This opens up to be sigma transpose inverse and sigma inverse. U transpose sigma transpose V X. Now I have U transpose got cancelled. So this is basically this X V. This changes to identity again. I have sigma inverse I up to k less than equal to k, and this is this. This is sigma inverse first k columns, k rows, and this is k cross k. I get I less than equal to k, which is x into v first k rows of v is h. Hence prove that H is a linear transformation. Now W was V. This H is a linear transformation of X. Hence H is a linear encoder of X. Proof. This is basically all the transformations I did in the previous slide, which is X transpose, X transpose inverse, and this is I'm multiplying all those, taking the first k rows or rows of the matrices wherever we get less than equal to k. This is simple transformations. So finally we get that X is the linear transformations of X and W. W was this initially. We took it. H was U V and H was U sigma and W was Without the Fourier's norm, we could not have been derived to the part that HW star should be equal to the SVD of x for the minimum square loss function, which was the most important part. Hence, all the four requirements were the most necessary required.